Hello, all. My name is Fernando Pavlovich. I am a professor from House University, Canada. I will be chairing the section, the graphic section on 2020 SIBGRAPI. Let me just explain the logistics. We have 5 papers, short videos of 5 minutes, and then followed by 5 minutes of Q&A questions for each one of the papers. So if you have any question, please use the chat. Don't wait to finish the video so you can type whenever you want. So if no further ado, let's start with the first paper. The title is Learning to Dance, a graph convolutional adversarial network to generate realistic dance motions from audio. The presenter is João Ferreira.
Imagine using your favorite song, like a salsa, for example. To create a set of body motions with a desired performance for that song. And then, with a set of images of you, create a video of you dancing that song without dance classes. In this work, we propose a new approach to synthesize human motion from music. Our approach has 2 main components: a generator network composed of spatial and temporal sampling operations and graph convolution layers, and a discriminator network that has the same layers of the generator, but using downsampling instead of upsampling. In order to generate realistic samples from human dance motion, we used an adversarial training strategy, where we train the discriminator and generator networks. To train and evaluate our method, we create a new dataset comprising common motions of 3 dance styles: ballet, salsa, and Michael Jackson. Our dataset is composed of 69 motion samples for training and 229 samples for evaluation. After training our networks, we generate a motion sequence by first classifying the audio and combine the audio class with a spatial temporal Gaussian noise. Then, we use the generator network to create a motion sequence conditioned on the audio data. Finally, we synthesize a video sequence of an actor performing the generated dance motion. We compare our method against the state-of-the-art method. Ballet dance comparison with dancing to music. Moreover, our method can change the style of the motions over time. In this sequence, we applied 3 different styles while generating the motion. Thank you.
Yeah, very nice paper. Congratulations. I don't see any questions on the chat, so I'll go with my questions. Waiting for some. I don't know if it's possible. I know that's not your goal, but imagine that you have a very good training set of a ballet dance piece. I don't know, Nutcracker or whatever, something simple. And if you get the same music and apply, can you recover the original dance? What's the error of there?
First of all, thank you for the compliments about the paper. And if I understand correctly your question, you are asking about if we can get the dance, the motion, and come back to the audio and synthesize the audio, for
No, no,
example.
no, no, no. I'm sorry. If you train your network in a well-known piece of ballet, for instance, so you have all the movements and you have the music as well. So can you, if you use the same music, are you going to recover the same motion, or what's the error when you try to recover?
I think I understand. Well, the problem we are trying to solve, we want to sample. So the final motion generated is a composition of motions in the training data set. So we will recover perfectly a sample from the data set, but we will recover pieces of samples and compose a new component. I think that's the answer to your question.
Okay. So have you tried, I don't know, for instance, I know that you have like some like three different styles, music styles. So have you tried to get another one that was not trained and throw in your network? What happened?
We do not report these on paper, but we have some experiments with another dance style that was country, if I not wrong. And the problem with that style is that the movements, the motions are not too characteristics. So it's difficult for a user to define if that movement was of country style. So we decided to remove that style from our experiments.
Okay, and yeah, I still don't see any questions, so I have a last question. Very very short. I see some artifacts when you recover. When you start trying to dance like Michael Jackson, it's just shortened. What are the problems?
Well, you say in the final video sequence, correct?
Yes.
Okay, we have to adopt the training of the video synthesis method that was video to video. Video to video normally is trained with 2D representation of the motion that is open pose, the same representation that we can synthesize now. And in addition, it uses a dense pose representation that is a 2.5D representation of the movement. We are not able to synthesize in test phase the representation of dense pose. So we have to adapt the train of V2V, and these artifacts are because of that.
Okay. Yeah, that's again very good paper. Thank you very much for the questions. I don't see any other questions. So let's move to the next paper. The title is Experimental Study of Volumetric Visualization of Black Oil Reservoir Models. The speaker is Leonardo Campagnolo.
In this paper, we made an experimental study on volume handling solutions for black oil reservoirs. We explored volume handling visualizations to provide better data inspection, enabling the generation of good quality views with focused information while keeping the context of the model. To store the reservoirs on GPU, we use a compact representation as a prerequisite. It also has the support for point allocation that solves the scalar field evaluation for different types of reservoirs. We then explored 3 different strategies to provide volumetric visualizations with good quality and interactive performance. We made a performance and quality comparison with our volume handling implementations using different view positions, showing the effectiveness of each method. We also made a visual quality comparison to show the limitations of each implementation in terms of scalar field evaluation. To enhance the quality of model inspection, we adapted an illumination technique that computes directional ambient occlusion effects. We then combined the results to produce interactive volumetric visualizations with directional ambient occlusion.
Okay, very good. Again, I don't see questions in the chat. Please, if you have any questions, go ahead. I have some very simple few questions, I think. I know that you have an experimental study, right? How does used in practice? You know, how these models are used in practice for oil reservoirs?
Well, I don't have much experience on how they actually used in the oil industry, but there is a lot of, they do a lot of simulations, and they want to, it's more about I don't think I can answer this because I'm not really in the area of the oil industry. I'm more about, I'm more related to how to visualize this data.
Mm-hmm.
So I don't think I can answer this.
You know,
exactly.
because my following question, it's related to the first one, because again, you compare different models, right? And then you say, okay, this model I can handle faster, and then I have another model with low quality, and so on and so forth. So, but I don't you need to think about the user requirements? So, what the specialist wants to see, or what I don't know, what is possible, what's not possible.
Yeah, I mean, we actually, I mean, in the beginning of the paper, we actually discussed that we usually have traditional viewer solutions. They actually are composed by maps, which only gives a two-dimensional views of the reservoir, and sections that it's like cutting planes, but it loses the context of the entire reservoir. And then we also have boundary views that usually don't show the internal parts of the reservoir. And when proposing a volume rendering solution, is like provide the visualization of the data inside the reservoir without losing this whole context, and also using the illumination technique to provide better shape and depth perception.
Okay. Yeah.
So it's much
yeah, it covers, because the point is, when you have clients, maybe they have like different requirements. So you can, I need something that's a real time, and my hardware is this, right? And but I can afford to have problems, to have, I don't know, errors or artifacts. And for some other applications, you you cannot afford any kind of artifact, but time and I don't know, raw hardware is not the problem. So my question would be like, okay, have you factored this into your analysis and say, okay, this is very expensive, but it's the most quality. That's more or less the line I was discussing. So I don't see any other question. I can have one more, and I know that you generate some visual representations, right? So and then you use some, you do evaluate this, okay, this is better, you see, and then you use the lab color pixel comparisons, and there are some things in the paper. So have you tested with users, to see if what you can, demonstrate on your lab color, it also is perceived by users?
Yeah, we actually didn't test it with real users. The only thing that we have is, as we use the GPU compact representation that also provides a point location algorithm, it gives to us the best possible result, like the ground truth. So we made that comparison with the other more simplified approaches that reached better performance. but we didn't make any evaluation with real users.
Oh, okay. Yeah. So I don't see any questions. I have my final question is what kind of hardware do you need to have like real time?
I think it usually depends on the reservoir. Of course, we have the bigger reservoir has like 6.2 million of hexahedral cells, and we made a test with 2080 RTX Ti, and we reached like 7 frames per second. So yeah, maybe on an older GPU it is really complicated to achieve interactive performance, but yeah, I think we need maybe use more other solutions to provide better performance in these cases.
Okay. Is there anything else you want to say, because the video was very short?
Yeah.
What was the hugest, I don't know, challenge?
Yeah, I mean, the real problem that we tried to solve is that the reservoirs are becoming bigger and bigger, and we have like we tested with 6 million cells, but with the increasing use of massive models, it is useful to have a solution that is capable to handle bigger reservoir. So we use this GPU compact representation as a prerequisite to use to have a really low memory footprint to be able to provide volumetric visualizations. So that was the idea, to use a really compact representation on GPU to make it possible to produce volume rendering visualizations.
Yeah, very nice. Again, congratulations for the paper. So I don't see questions, so let's move to the next paper. The title is "What Questions Review About Novice Attempts to Make Sense of Data Visualization, Pattern and Misconceptions." The paper will be presented by Ariane.
Hello, my name is Ariane Rodrigues. I am a PhD student at PUC-Rio. Today, I will talk about patterns and misconceptions revealed by questions novices ask when making sense of data visualization. Researchers have been striving to develop new tools and visualization techniques to support analysts in extracting information and gaining insights from the data. We still need to face the challenge of ensuring that both the producers and consumers of data visualization can understand them. In this paper, we aim to investigate what people understand and misunderstand about certain visualizations. We investigated the initial questions people make when first encountering a visualization. We generated a set of visualizations, and through a user survey, we requested participants to ask questions about each visualization. After analyzing the resulting questions, we standardized them, derived templates for the recurring types of questions that we identify as information-seeking patterns, and classified the various kinds of error participants made when creating the questions. We conducted the study through an anonymous online questionnaire. We presented all 20 visualizations in random order, one at a time. For each visualization, each participant created up to 5 questions about the underlying data that could be answered by examining the visualization. The questionnaire collected a total of 1,058 answers. We examined the collected data and discarded 8 non-questions. We created standardized versions of the questions. The guiding principle to standardize was to rephrase each question following basic English grammar. We rewrote 800 sound questions. We generated a consolidated list of 249 unique question templates, resulting in at least 5 question instances per visualization. We abstracted the standardized questions as parameterized templates, replacing the variables' names with their corresponding types. We also parameterized questions variations. We also flagged 250 questions as problematic, which means that those question instances could not be clearly answered by inspecting the visualizations. We individually recoded the questions and discussed the code definitions again in 3 more iterations until we were satisfied and had a substantial agreement. We raised a unified set of 20 codes, categorized into 5 major classes I will describe in the next slides. In 88 cases, there were comprehension errors about the variables represented in the chart. It was related mostly to treating a continuous numeric variable as if it were discrete. In 41 cases, the questions were ambiguous, meaning we could assign different interpretations to it, each with a different answer. For instance, in a Sankey diagram, a participant asked for the intensity of the relation without specifying the relation they meant. In 43 cases, the questions were difficult to answer. It was related mostly to questions that inquired about the size of specific segments, which are often not straightforward to answer with this type of visualization. In 28 questions, participants posed questions that the visualization could not answer. It is related to questions that require observing individual objects or computing the right values from them, which are not represented in the visualization. In 79 questions, participants failed to follow the instructions when filling out the questionnaire. We asked them to pose questions about the underlying data and not about the chart or any imagined domain. For example, assuming that the numeric variable represented the population of each country. To summarize, after collecting 1,058 questions from 22 participants, we classified the questions into two groups: clear and conceptually sound, and problematic. We derived 249 unique question templates from the CLEAR group that describe the different types of 54 questions people are expected to answer through each visualization. We applied an open coding technique for the problematic group to identify the types of problems found in the questions, yielding 20 types of problems subsumed under 5 classes. The study results reported in this paper can be used in teaching data visualization, as they uncover and classify frequent errors people make when thinking about data represented visually. For example, we can use these to create better charts, maybe with annotations that teach people how to read them. These results can also inform the design of visualization recommender systems, going beyond the association of the variable types with visualizations, through supporting the question-answering interactions more fully. They can also help users formulate better questions, providing more in-depth data analysis experience and more effective information seeking. Thank you.
Again, thank you for the paper. It's a very nice one. Again, I don't see questions from the audience, so I have many questions about this. Okay, I've been working with visualization in those visual analytics thing, and I see that you mentioned that, okay, your findings can be used to help, I don't know, teaching visualization. Can you elaborate on that? Say, what do you think?
Okay, so we encountered a lot of errors people make, and I think that this could be used to teach how. If I know that some bar chart brings some wrong questions, maybe I can use this as example for this student or novice to identify, how can I say, make it clear to see the error and how it could be correct. I don't know if I can explain.
Because I think it's fascinating the work you have done. So, okay, trying to find like questions and then validate those questions in practice. So I've been thinking, okay, and you mentioned, okay, this can be applied to teach visualization, and so, okay, that will be nice. If you have, I don't know, a list of recommendations, I don't know if it's in the paper or if you have any kind of supplemental material, but that will be very good for the community as a whole. So we have a question from the chat. What was the background of all the participants? I think it's about the 22. Did they have any anterior knowledge on the subject?
Yeah, they are students of our university, computer science, informatics, and they are graduate and undergraduate students. So they took 2 classes. I'm sorry, and the long video has this information. And they took some classes about visualizations, and then they performed the questionnaire.
Okay. Yeah, I think we have another one here. Yeah, how do you avoid biases in the questionnaire?
I'm sorry?
How do you avoid biases in the questionnaire?
I don't think I can see some biases. Can you make an example?
Yeah, I don't know who has asked it. In terms of bias, I don't know exactly what I think it's Luis and Figueiredo it's talking about. So, Luis, if you can elaborate that, I have another question. Then you get back to this one.
Okay.
I have another question. Is okay. You find something. Okay, that people makes more mistake with this than that.
Mm-hmm.
Have you studied the connection of this with the Gestalt theory or perception theory?
No, not yet, but it is a great path.
Because some examples that you give can be explained by the perception, right? So if it's okay, bars are better than maps. People tends to do something. So that's how can you haven't tried to check that?
No, not yet.
Yeah, no, I think that's very important. It can be a follow up, just because I've seen most of my uses are based on this perception thing. But that's fine. So Luis said that this is exactly the problem, and he can walk through offline and talk to you later. So any other question from the audience? If there is any other question, I can go with my questions. There are some papers that I like, which try to recommend visualizations based on data, right? So I don't know, 4 papers about that. Do you think you can apply your discovery, is not your approach, but your discovery to recommend visualizations?
First of all, the difference between these papers you told and ours is that our data was we tried not to put information. The variables are very they didn't have a word in Portuguese or in English, so we tried to extract the question just looking at the visual. So I think the first difference is that. So I don't think we can recommend yet because we don't have actual values and data. So I think it's another step that we can go ahead.
Okay, I think we have time for more. Just one question. So I have, what is the breakthrough discovery? What you say? Okay, wow, this is nice.
The breakthrough discovery. I think people try to make sense, put sense in the data. As I said, we didn't use real names, so some students try to make questions using that names. So we found COVID, for example, and I think when they can't make sense of the visualization, they try to bring to some place near. So I think this was a surprising point.
Yeah, I remember the example of map that people say about population, but there is population. That's very interesting. Thank you again for the paper. It's fascinating. Let's move to the next presentation. The paper is titled HankVis, a visualization framework to assist interpretation of learning to rank algorithms. It's going to be presented by Matheus Pereira.
Hi, my name is Matheus. Today I'll present RankVis, a visualization framework to assist interpretation of learn-to-rank algorithms. This work was part of my master's thesis, supervised by Dr. Fernando Paulovic at Dalhousie University. You can visit the Visual Analytics and Visualization Lab website with the link in the description. This work was supported by MITEX through the MITEX Accelerate program, with partnership of Waterford Energy Services Inc. We acknowledge the support of the Natural Science and Engineering Research Council of Canada. Machine learning is currently applied in many fields, but still often used as a black box and lacks transparency. Learn-to-rank is the application of machine learning to create models that can rank elements. There's a lot of research on improving these algorithms, but very few on transparency and interpretability, which is the focus of this work. We use a model based on trees, and although there are frameworks for interpretation of tree-based models, they do not focus on the ranking aspect. We contribute with a visualization framework to assist in the analysis of learn-to-rank algorithms, proposing three visualizations that allow various analysis of the ranking, including feature contributions, interpretation, and change over time. 4 design guidelines were considered for our proposed visualizations. First one is ranking order. The primary purpose of learn-to-rank algorithms is to rank elements. Therefore, the visualization should always reflect the ranking information. The second one is ranking progression. Given the iterative nature of the employed algorithm, we want to support the analysis of ranking changes over time so that model progression can be investigated. Third, feature influence. The algorithm uses data features to rank the instances, so assistance should be provided to understand how individual features influence the instance's ranking. And last, ranking explanation. The rank positions are not defined by features in isolation, but through their combination. Because of that, we need to support the analysis of the complex interplay among features to aid in understanding how they are combined to define the instance rank positions. Now let's take a look on the visualizations. RankDiff displays ranking order change and also displays change over time in the form of trails. This visualization is model agnostic, since the only information used is the ranking order. The instances are displayed in a grid, being positioned on the horizontal and vertical axes based on the previous and current ranking order. For instance, on the left, we can see a set of results in a diagonal. This happens because both axes are using the same ranking order. Now, consider that a new ranking order is defined for the vertical axis. The elements start to move up or down to their new ranking position. Then, to realign the results, we update the horizontal axis to follow the same ranking order. By doing this iteratively, we can see the ranking changes over multiple iterations. The second visualization is feature gain, which is used to visualize individual feature contribution to the ranking. Each square represents a data instance, using its feature value to position it in the y-axis and the ranking order in the x-axis. The arrows show the contribution to the ranking that the feature provides. We can create a cell like this for each feature. On the top, we display the feature name and its importance. To allow comparative analysis, the data is split in 3 groups: the top-ranked instance, the bottom-ranked instance, and other relevant instances that do not appear in the previous groups. To generate this visualization, we need to find the individual contribution of each feature for every instance. This is done by summing the contribution score of every path on the trees that rank an instance, which consider the feature. We can also use this number to find the overall feature importance by summing the absolute value of the individual instance contributions. This example shows how the same set of instances can be viewed through the perspective of 4 different features. The third visualization is rule gain, which gives a better view of rule contribution through a cumulative bar chart. This allows us to compare the elements and see what rules cause the ranking differences, and then see why one instance was ranked before or after another. The instances are displayed from left to right, following the ranking order, and the rule contributions are displayed below. When a rule contributes to the instance score, the bar chart for that instance is modified, either increasing or decreasing. On this example, we can see a set of 6 rules on the left, and how they are applied to each one of the 3 documents on the top. Bars with a darker color indicate that the rule was applied to that instance. The rule color indicates whether it contributes to a positive or negative score. With RankVis, we propose 3 visualizations following 4 design guidelines focusing on the interpretation of learn-to-rank. We show how these visualizations can be useful with 2 case studies, one that reviews flaws not directly visible on standard metrics, and one that shows how these visualizations can be used to interpret the ranking, revealing relevant features and how the ranking is composed.
Okay, thank you. It's okay. We don't. Yeah. Okay. Great. We have a question from the chat. How did you come up with these guidelines? Was your idea, or did you use some literature? And do you think they fully represent the problem?
These guidelines were developed during the study. So this study took a very long time to develop both the visualizations that we created and how we wanted to evaluate this. It was a very long process. like there is a specific direction, but there were some other papers that talk about different styles of visualizations used for showing, especially on bar charts and the interpretation they provide. And there are other studies about showing how to say interpret rankings, but not in using a learn to rank algorithm. So like all of these were used to define these guidelines.
Do you think they fully represent the problem?
Well, they definitely capture what we wanted to see, because learn to rank interpretation is something that honestly we didn't find anything in the literature. There was just one paper that tried to deal with this problem, but their focus was still a bit different. We discussed this a little bit more on the paper itself. So for our purpose, that was interpretation of learn to rank and be able to explain difference between elements and see exactly where they differ and features that are important, and see how the evolution of the ranking happened, because we are assuming an iterative scenario. So these guidelines focus on these points.
Okay, I don't see any question I have. It's strange to make questions, but that's fine. It's part of the paper. But anyways, I think it's linked to this question. I would ask you to tell this story. Why do you start with rank? Who's behind that company? What they are trying to do? And then we had what we developed an algorithm, and then we find bugs in the algorithm using this visualization. Can you just go through the story to?
Right. So this work started with partnership with Waterford Energy Services Inc. They're a company that operates in the oil and gas industry, and they wanted to create a new way to search the historical data that they have. So we wanted to create an interactive learn to rank algorithm so that they could iteratively search and say what was relevant or not for their specific issue. So we developed a iterative version of the learn to rank called LambdaMart. So we had an iterative version, and then we wanted to make sure like how it was working and see if it was working properly. So we started to create these visualizations to actually understand what the algorithm was doing. And we show in the paper one use case about like actually seeing the visualization working iteratively for a few cases, and we see a problem, and basically the algorithm could get stuck in some cases, and that's something that we see because of the visualization, because on the metrics that you use for evaluation of learn to rank, this is not obvious. On the metrics, it seems to be okay, but if you actually see the results, they're not so good.
Okay, yeah, no, that's that. I think that summarized really well the paper, at least for me, that I know the paper. Yeah, I don't see any other question, and thank you very much, Matheus. Let's go to the last paper now. Global illumination of non-Euclidean space. It's going to be presented by Thiago and Luis Velho.
Hi, we are going to talk about global illumination of non-Euclidean spaces. Here, we take the challenge of computing the global illumination in non-Euclidean spaces using a path tracer algorithm. In such spaces, the concept of photorealistic rendering is not well defined because there is no real camera there. However, the possibility of defining global illumination equation in non-Euclidean geometry opens up the door for path trace generalization.
The main contributions of our paper are the introduction of the remaining global illumination through a generalization of the inner product term of the rendering equation by the Riemannian metric, a path tracer algorithm to approximate the solution of the remaining global illumination in space modeled by Thurston geometries, a pseudocode and implementation of the algorithm GPU using RTX, The implementation considers only space modeled by the Pearson classical geometries. Finally, we apply the non-Euclidean path tracer to render photorealistic inside views of the 3D fractals, Poincaré sphere, and the hyperbolic mirror dodecahedron.
We now present some results of our implementation. This image illustrates the immersive visualization of the three-dimensional fractals using the path tracing algorithm. On the left, an outside view of the embedded corner box showing how the fundamental domain tessellates the space. On the right, a closer view of the specular spheres embedded in the scene to show the tessellation being reflected on their surfaces. These are immersive views of the Poincaré sphere. The face identification produces a tessellation of the tree-sphere by 112 dodecahedra. This is one of the four-dimensional regular polytopes. On the left, the scene is composed of a single cowl, a pentagon floor, and 4 spheres. It also includes the edge of the fundamental domain to show the space structure. Looking towards a dodecahedron face, we see copies of the scene rotated by p by 5. Note that as the distance increases, the scene size first decreases and then begins to increase. There is a large cowl upside down in the background. On the right, we increase the specularity of the pentagon floor and replace the scene by a single specular sphere in a single monkey's head, which is the Suzanne classical blenders mesh. Again, as the distance increases, the Suzanne size first decreases and then increases. The dodecahedron edges are removed. The last example is the inside view of the hyperbolic dodecahedron. On the left, the scene is composed of a Suzanne, a specular sphere, and a pentagon floor. We add the fundamental domain edges to highlight the hyperbolic space tessellated by right-angled dodecahedra. The image is the inside view of the hyperbolic space quotiented by the discrete group generated by hyperbolic reflection of the dodecahedron face. On the right, we only removed the dodecahedron's edges. Thank you.
Thank you.
Thank you.
Yeah, thank you for the presentation. Sorry, I have forgot to announce Vinicius as well as a presenter. Sorry, Vinicius. Yeah, I have plenty of time for questions. I don't see any question. It's not my area of expertise, so I'm trying to learn something. My first question is, okay, what are the advantages of using a non-Euclidean space versus a Euclidean space?
Luis, may I?
Yes, sure. Go ahead.
Well, because you cannot visualize non-Euclidean spaces using the traditional methods used for visualization Euclidean space. So if we would like to visualize such space, we have to implement the techniques, develop the techniques to put a camera inside the such space. So you can use this for education, for maybe special effects or games.
So that's not possible to do with Euclidean space. That
is not possible to do.
Okay, fair enough.
Because there is the metric. For example, in the sphere, the metric, and in the hyperbolic space, the metric is different. So you cannot use like the classical Euclidean metric, and the topology is also another problem, because you have to model the topology of the space, and in Euclidean space you can only model a few topologies.
Okay.
In three-dimensional.
Yeah, let me just add some comments to what Thiago said. This work is actually part of a large research that we are doing at IMPA, and then is about visualization of mathematics, in particular to visualize 3D manifolds. 3D manifolds are important object in mathematics and also in physics, because they pose the question, what's the shape of the universe? Because we are used to a geometry that's flat. The Earth actually has a curved geometry, but we see the Earth, locally, and everything looks flat. But if you want to kind of do something intrinsic on a sphere, then it's a different thing. So mathematicians study different types of geometry. And then, you have like the classical geometries that exist in 2 dimensions and 3 dimensions. So there is the flat, the spherical, and the hyperbolic. But then you have, like in 3 dimensions, 5 more geometries. So these are the Thurston geometries. And this is related to the Poincaré conjecture, and actually was on the Millennium Problems in Mathematics that was solved like a few years ago by Perelman, a Russian mathematician. And actually he won $1 million prize because of that. So it was the first a problem from several Millennium Problems that was actually solved. It was a surprise for the committee. And so since then, mathematicians have explored this not theoretically, but also concretely, and to visualize those spaces like a really important. Mathematicians and people from other areas of science and physics, as I mentioned.
Okay,
so,
yeah, I have a question related to that.
Yes, yeah.
It's actually from the chat. Are there any user studies on how people can learn to walk in non-Euclidean space using immersive visualization? Perhaps you, from your mass exhibition. Again, for me, is that it's linked to that. You are going to show some. I perceive the world, I think, as a perception, as a Euclidean thing. But then you're showing through a non-Euclidean map. So how there is any kind of user study to show problems there, or?
Well, we are actually developing this kind of user study. And there are like a few people. This is actually a really hot area now in the world. I mean, there are I would say 3 groups that are intensively researching this, and we've been communicating. And our group at IMPA, I think, is the most advanced because we are the ones that are doing this using virtual reality and real time, exploiting all the capabilities of the new architectures of NVIDIA GPUs for ray tracing. So we are the first to use ray tracing for this kind of visualization. And now we are the first to use real-time ray tracing in virtual reality. And there are a lot of very profound questions because, as Thiago mentioned, the metric is totally different. So, it's not the Euclidean metric. And then there's also, the curvature. It's not flat as we are used to. It's totally curved. And for certain things, I mean, you need to, adapt the way the user behaves in this world because we are used perceptually to a flat world. And then you have to get used to be in a different type of world. So we are doing a lot of research on that, but there's no conclusive, findings yet. But on the other hand, I mean, it's really striking when you put your headset and you are totally immersed in this, because the only way to visualize this kind of 3-dimensional manifolds in an intrinsic way, being inside, right?
Okay, very nice. I have one last question from the chat, a quick one, I think. How the discretization of the tessellation affect the performance of the method? What was the size of the models?
Actually, there's no discretization in it because we simulate all the geometry. But what happened is that differently from traditional ray tracing in a flat space, in Euclidean space, the rays are straight, straight lines. In curved space, in a non-Euclidean space, the rays in general are curved. And so the equation of the ray is not as simple as for the Euclidean case. So the equation of the ray is actually solved by a differential equation, an ordinary differential equation. And so for that, we actually use either closed form solutions in some cases to intersect with the geometry, or we use like ray marching, doing integration along the ray and then testing for intersections. So in that case, I mean, I wouldn't say it's a discretization. It's like when you use ray marching, we are actually computing a solution, in a piecewise linear manner, right? So there's no, and what I guess the question is referring to is like, because of the geometry and the topology, let's say a simple case, when you have like the 3D torus, so basically we are visualizing the torus from the inside, right? It's like, let's say the 2D torus is a donut, right? And like a ray in a 2D torus, it goes in a curved way, like around and like that, right? So if you are looking at something in a torus, you have many copies, right? So in that setting, basically you have the concept of the fundamental domain is just a square, and the fundamental domain, when you kind of fold it like this, becomes a cylinder, and then you fold, becomes a torus. So it's the same in 3D. For like the 3D torus, you basically glue, the opposite sides of the cube, and then when you look in this space intrinsically, you see many copies of this fundamental domain, because the rays go around, right? So what I guess the question is referring to is like this, grid that is seen in some of the images. And so, but this is like an effect of the topology of the space. And in the case of the, flat torus, the flat 3D torus, the geometry is flat. So it's the same as the Euclidean one. Only the topology is different. Okay. But as Thiago mentioned and showed in the images, like in the sphere and then in the hyperbolic cases, so everything is curved. Okay. And you get a lot of strange effects, like as things goes to farther, they become smaller, then becomes bigger. There's no it's a different type of perspective.
Okay, no, thank you very much. The fascinating work. Thank you all the presenters, and thank you the audience. We are closing now. We are ahead of time. Thank you very much, and see you later. Bye-bye.